So let's start by digging deeper into some basic machine learning classification models. In this session, we're going to see some classifiers, we're going to talk about naive Bayes, we're going to talk about some linear classifiers, logistic regression, and support vector machines. We're also going to talk about some nonlinear classifiers, neural networks, support vector machines. Again, they have both a linear and nonlinear version, Gaussian processes. And finally, we're also going to talk about lazy learners and ensemble modeling. So let's start with the linear classifiers. We've seen this graph in a previous session as well, and here we have a scatter plot, this fictional data set with two variables, email length and new recipients. So we have two classes, spam and ham. You can assume that the red class represents spam emails and the orange data points represent ham emails. So given this graph, given these two variables, given these two classes, and someone asks you, okay, how would you classify this data? Think about it. Well, it's very easy. You can just draw a line between these data points, and there you go. You have the red class and you have the orange class, and they're perfectly separated by a line in the middle. So when a new email is sent, it's very easy to see on which side of this line it belongs and say, hey, this email looks like it's spam or it looks like it's ham. So a way to do this, a way to draw this line between the data points is through a model called logistic regression. Logistic regression is based on the logistic formula. As you can see, this is the formula up there, and you can also see a graph of it there. So this function, the logistic function, outputs a number between 0 and 1, but it can receive as an input any real number. So let me break down this formula for you. What this means is that the P of y given x, that is the probability of our target given x capital, where x is our input data, is defined by this. So this is again the logistic function. And as you can see, this summation here is a summation over all the different variables, x1 being a variable, and W1 being a weight associated with this variable. We'll see a worked example in the next slide. Logistic regression is considered a discriminative classifier. This means that it learns how to separate between classes, but it does not build an explicit model of those classes. So it can't tell you what spam looks like or what ham looks like, but it can tell you that, hey, this new data point should belong to ham and this new data point should belong to spam. So how can it do without building a model of the classes? As we saw, logistic regression just draws a boundary between the different classes. We'll see another model later on, naive Bayes, which instead of drawing this line, it builds a model of each class. So it can tell us what's the probability of a data point belonging to each class. So again, this is another example of logistic regression and how the logistic function separates examples into. So here you have only one input variable, x, which ranges from 0 to 1 in this example, and y is our target variable. So in this scenario, you have two classes, but you have only one variable, and you can see how logistic regression would break down the two classes. So let's see a worked example together. Let's say that you have two variables, the age and the income, measured in thousands, and you want to predict the probability of someone buying a particular product. So let's revisit our formula. The formula, as I mentioned, is P of y given x, where x, in our case, the dataset, consists of the age and the income. So taking a look again at our formula, we have this summation here. The summation from I equals 1 to I equals n of wi and xi. What this means is that you need to find out a coefficient wi for each variable, and then you need to multiply this coefficient by the variable value and add them all up. So let's move on. As I mentioned, we have the age and the income, so x capital refers to age and income, y is the probability of purchasing a product, and you ran an optimization algorithm for logistic regression, let's say gradient descent, and you found that the coefficient of age is minus 0.348 and the coefficient for income is 0.39. So what this means is that the older someone gets, the less likely they are to buy this product, but the higher their income, the more likely they are to buy this product. So these two variables work in opposing ways. Let's see what happens if we choose a particular user. Let's say we have a user that has an age of 23 and an income of 25. Again, the income is measured in thousands. So in this case, we take this formula here because we calculated the wage, and then we replace age and income with the values of age and income. We do this, and what do we get back? We get back a probability. We get the probability 0.85, and it's more or less that. And this means that the probability of someone in our database that has an age of 23 and an income of 25,000, the probability of buying is around 85%. As you can imagine, you can replace many things here, like you can add more variables, maybe the coefficients would be different, but this is what logistic regression breaks down more or less. This expression here ensures that the output we get is between 0 and 1, and in this parenthesis, this is where the magic essentially happens. So this was a brief overview of logistic regression, and now let's move on to naive Bayes. So now we're going to talk about the naive Bayes model. Naive Bayes is based on Bayes' theory. So this is due to Reverend Thomas Bayes, who lived around 250 years ago and came up with this formula. This is the formula for what we call conditional probability. It tells us that the probability of A given B equals the probability of B given A times the probability of A over the probability of B. This is one of the most important formulas in machine learning and statistics. So Bayesian statistics is a whole different, I wouldn't say different field, it's a different approach to statistics based on the notion of probability being subjective belief. And Bayes' formula can be very helpful in many different situations where we have prior beliefs, but not only. So naive Bayes is one such example. It's a very simple classifier which can work very well in practice in many problems. It's very easy to train, very easy to execute. And because it's a very simple model, it can be a good benchmark for more complicated models. You always want to start with simpler models, use this as a benchmark, and then see how well more complicated models fare against them. So naive Bayes is a generative model. So we saw logistic regression, which is a discriminative model. A discriminative model draws a boundary between classes. A generative model, on the other hand, creates a model of each class. So it has a notion of what spam looks like and what ham looks like, and then it can attach a probability to each new data point of it being ham or spam. So generative models are called as such because by being able to specify a model of what a class looks like, we're also able to generate examples from this class. This is something for which naive Bayes is rarely used in practice. However, neural networks, which can also work as generative models, are quite often used to do things such as generate images or generate text or audio. This concept of generation has its uses as well. So, Bayes' theorem, let's try to break it down. As I mentioned, this formula means that the probability of H given D or A given B, in this case, we use the letters H and D because this is our hypothesis and this is our data. So we have a hypothesis that, a new data point belongs to class A, for example, and then we have some data. So the probability of H given D is equal to this expression, the probability of D given H times the probability of H over the probability of D. So the probability of H is what we call the prior. And that the prior is what we believe before we saw any evidence. So what's the probability of this hypothesis being true in any case? So for example, let's say that 10% of all the emails we receive are spam. So without knowing anything about the problem, the prior tells us that, hey, 10% of the emails are going to be spam. So this is what we call the likelihood. So the likelihood is the probability of the data given the hypothesis. So if, for example, this email is indeed spam, then what is the probability of us really observing this specific data? And this is a normalizing constant. So this is the likelihood of that evidence under any circumstances. That is, what's the probability of observing this data under any circumstances, whether it's spam or ham. In essence, in our calculations, we treat this as a normalizing constant, which means this is a number that is used to divide this expression up here in order to make sure that it's in this expression is between 0 and 1, because this needs to be a probability. Naive Bayes is a classifier, so what's our goal? So our goal is to predict the class given a set of inputs. So given the previous expression, how does this break down in our case? So we have the probability of a class, could be the 0, 1, 3, again, spam or ham, for example, given a set of data. So variable 1, variable 2, blah, 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 variable n. So the probability of our class given our data is this expression. So you see that this expression here corresponds perfectly to what we saw earlier. So this denominator here, as I mentioned, is a normalizing constant. So we don't really care about this. We care mainly about that. So this is going to be different for each class and its different set of data points, and we can safely ignore this. We can safely ignore the denominator. We're interested in the numerator, which, if you follow the rules of probability, you can just take my word for it. It can also be expressed as this. This is the joint probability of the class and all the variables. So this means that the probability of seeing this class and also seeing variable 1 having a particular value and variable 2 having a particular value, etc. So just to revise what we did. We started with this, we broke down this expression, we said we ignore the denominator because it's a constant, and this expression breaks down to this when we try to calculate it. Again, just take my word for it, we don't need to go into much details, and now we want to calculate this. And what's the problem? So again, if you follow the rules of joint probability, this breaks down in a very complicated expression. This breaks down in an expression where you have to calculate the probability of each variable in this expression given all the others. That is the probability of x1 given x2, blah, 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 the probability of x2 given x3 and class and all that, and it goes and on and on and on and on. So essentially, what this expression tells us is that we need to calculate the interdependencies between every and all variables until we start with x1 given all other variables, x2 given the other variables, until we end up only with a class. And the problem is that this is what we call intractable. Even for a few variables, let's say 10 variables, we end up with a combination of thousands, and it's very difficult to see how to calculate this. So this is where the naive part comes in. The naive Bayes makes this assumption, which is called conditional independence. So this means that this expression can be simplified, and if we're given the class, then the rest of the variables are completely decorrelated from each other. So this expression x1 given all the other variables in the class is equal to x1 given the class. We assume that the class gives us all the information we need in order to understand what the value of the variables is without really caring about how one variable influences another, because all these influences come directly from the class. So coming back to what we wanted to calculate, the probability of the class given a set of variables, this then breaks down as follows. Z is a normalizing constant, again, let's ignore it for now. And we have the probability of class, which is the prior. This is what's the probability of getting this class before we see any data. Again, as I mentioned, if, for example, we see that the probability of getting spam is 10%, 90% for ham, times the product of this probability, xi given ck. This is the probability of observing a specific value given a class. So the probability of observing that variable 1 takes a specific value given the class. So basically we've simplified this expression down to this. So we've eliminated a huge number of the calculations that we need to do. This is what naive Bayes looks like. If we didn't have naive Bayes, we would have to draw arrows between all those different variables and assume that x1 is related to x2 and x2 to x3 and all that. Whereas with naive Bayes, we assume that there is a class, and the class is what determines the values of all the other variables. This means in practice that naive Bayes is very easy to run because the calculations are much more simplified. It's very resistant to overfitting. So naive Bayes is a very strong assumption, which means that if there are any intricate or noisy patterns in the data, let's say interrelationships between 2 or 3 or 4 variables, naive Bayes will completely ignore this. However, the naive assumption is naive indeed. So if we really face these problems where there might be interrelationships between the data, where x1 can influence x2 and then this can influence x3, etc., the naive Bayes will fail to capture this. So think about it for a moment. Let's say that you are trying to classify the different types of text documents. You would expect that football as a word will occur more often with kick, and also basketball might occur more often with dunk. So you expect these interrelationships between variables, between words in this example, and naive Bayes cannot really take this into account, even if in practice it works quite well for many problems, especially text classification.